projects you make with thinking tasks. All like trying to get over it.
Last time I did my shoulder popped out.
I wouldn't like that.
Okay, so a couple of announcements. First of all, I made a change to homework 1. Did you get it in your email this morning? So when I make changes to homework assignments and it says send it to everybody, it doesn't come to your email.
So this morning when I checked, I didn't see anything. But then I looked on Canvas and I saw the change.
So you looked on Canvas,
Just separately to get the homework.
but it doesn't. But it doesn't. It doesn't send it out to you.
I did not. I don't see it.
Yeah, I don't know if it'll do a change, but if you uploaded it, it probably does. But maybe just
I did. I checked the box that says inform people of the change.
preference I have.
So you got the email?
No.
No. Okay. All right. So that I was pretty sure that it would probably be messed up. So so what I did was I decided, since there's a due date coming up, and I wanted to reduce the amount of work you have to do. Well, I'd love it if you spend all the time you do on systems like electricity and magnetism too, for my course. But that's a required course in my courses. So what I did was I said, you've got free homework for homework 1. So all you have to do is just do one of them. Okay? You can choose whichever one you want. The other 2 are optional. I mean, of course, it'd be great if you did all 3. You'll learn much more. But you can choose whichever one you want to do, which you think is the most interesting. You have to do all of them.
What?
So you have to be prepared to grade all of them. So you have to do all of them. Okay? So that's the first thing. So there's only one problem. Next thing is, I think you have received an email, something about course evaluation. You did? Okay. Okay. So those of you who received that, okay, you absolutely have to do this, okay? Okay, because I got into trouble because I never tell people to evaluate the course. And then if the course is not evaluated and not reviewed, then people will not know if it's a good course or not, okay? So it's really important to me that you review the course. Okay, you can say the course is terrible and the professor wears lousy t-shirts and makes bad jokes, whatever you want to say, but please evaluate the course. Okay, last quarter the course was evaluated by 75% of you, and you all said very nice things. So that was great. I appreciate that, and it'll be helpful for the future. But please, I don't know why they evaluate the courses twice. I guess they do it in the middle and then at the end. Is that right? Yeah. So just do it. Okay. It won't take you very long to click through. Okay. All right. So any other things? I've pushed Zoom, and I am recording it, which is what this thing says, right? Yeah.
That just means the screen is sharing.
That just means the screen is sharing. Let me just check.
Oh,
it is recording. Okay. Okay. All right. So last time we talked about Goldstone modes. So let me just quickly remind you what we did very, very quickly. I'm not going to go through it all in great detail. So we started off with a Hamiltonian for the ON model. What we did was we computed the partition function, and then we computed the susceptibility tensor, which is how much the spin component in direction alpha depends upon the field applied in direction beta. And it was like this. And then what I showed you was we cranked away on this term. And I showed you that it had the following tensor structure, a thing that it looks like this, and then a thing that looks like this. This is the transverse part, this is the longitudinal part. And we calculated the function form of chi-parallel and chi-perpendicular. And what we found was that chi-parallel was just the same form that it has for a system that is a scalar, a discrete order parameter, d2f/d8 squared. But chi-perpendicular had this following form, and it's just given by the ratio of the magnitude of the ordering divided by the external field, and M alpha was ordered in the direction of the applied field and the magnitude M. So that's what this thing is. We also we reminded ourselves about the static susceptibility sum rule. So we showed how the susceptibility, which is a thermodynamic quantity, is related to the k equals 0 component of the correlation function for the fluctuations in the system about mean field theory. If you're above TC, the mean field theory is just the order parameter is 0, so it's just the order parameter correlations. Below TC, it is the fluctuations about the mean field value, which is some value given by the minimum of this potential here, and then you look at the fluctuations about that, and so the transverse correlations related to the static susceptibility, longitudinal correlations related to the longitudinal susceptibility, and so what we saw at the end of last lecture was that if I'm below TC, H is equal to 0, so I take the magnetic field, centered equal to 0, and then M will stay non-zero, and that means that if I look at the chi-perpendicular, it's going to be the ratio of M over H as H goes to 0, so it's going to be infinity. What that tells you is that the correlation function is inverse for large k equals 0 is equal to 0. And this infinite susceptibility tells you that, that you just have to make a tiny nudge in the system and it will make it have a finite change. And the reason for that is just because I've got this minimum around here. There's an infinite number of degenerate states of the system. And so when I make a transverse field, a transverse field which changes the direction of ordering, that costs no energy for k equals 0. Then we argued, well, what happens when k is non-zero? So when k is non-zero, well, what we expect is that if I'm now, that means I've got a transverse wave that has a wavelength which is finite. And if that wavelength is very long, if it's infinity, then we know that there is no cost. If the wavelength is now not infinite, but finite, well, what that means is that the grad S squared term in the Landau free energy will now be non-zero, and so that will contribute some energy to the system. And so what we then see then is that the energy spectrum of the system might be expected to be proportional to k squared, but certainly is going to be going to 0 as k goes to 0. And so these are the transverse modes, and they are gapless, and they go to 0 like that, and they're called Goldstone modes. And then we asked, are there any examples of this? So we came to comparing the sound waves in a solid compared with a sound wave in a liquid. So I had to look at sound waves in the solid like this. There's longitudinal and two transverse modes. And as omega will go to 0 as k goes to 0. So the energy of those modes goes to 0 for long wave. So all of these modes, longitudinal and the two transverse ones, are going to 0 as k going to 0. That means that they're acoustic modes. They're sound waves. Omega squared goes as c squared k squared. Okay, that's what a sound wave is. So an acoustic mode will go to 0 as k goes to 0. But it doesn't mean it's a Goldstone mode. And which ones are Goldstone modes? Well, it's only the transverse ones. And how you know that they're Goldstone modes is that for T greater than the melting temperature, the transverse modes don't exist in the liquid, but the longitudinal ones do. And so the longitudinal sound wave in a liquid is not a Goldstone mode because that's there above TC as well. Only the modes that are the consequence of spontaneous breaking of a continuous symmetry are Goldstone modes. So this is a very trivial example, sound waves in the solid, but the same thing applies to condensed matter systems and field theories and so on. Okay, so that's where we ended last lecture. And what I want to do today is I want to talk about what the correlation functions look like below TC. So what we're going to do is we're now going to step back and we're going to go and actually calculate what the correlation functions look like below TC. We're going to see how rigidity emerges, and we will then look at the lower critical dimension of these systems of continuous symmetries and see why 2 is the lower critical dimension. So let's get started. So what we're going to do now is we're going to answer this question by doing an honest calculation. So let's just remind ourselves what is the strategy of the calculation. So the strategy is this: is first of all we're below TC. So what we're going to do is we're going to have to look at the fluctuations about mean field theory. So first of all, we need to find mean field theory. So the first thing is step one is going to be to minimize the effective free energy and our free energy. So we're going to minimize the free energy to find the spatially uniform state. And in this spatially uniform state, the expectation of M is going to be non-zero. So the system will be ordered. So we're going to first of all find out what that is. Then what we're going to do is we're going to compute the cost of a fluctuation, compute the free energy cost of a fluctuation. And we're going to do this in the Gaussian approximation. And once we've done that, remember we did this last week. We showed how we could compute fluctuations by just from looking at the free energy, we can then read off what the correlation function is. We don't have to do any other calculation. So we work that out from the equipartition theorem and so on. So then what we're going to do is read off the correlation function. Okay, so let's do step one. So let's write down what the free energy of the system is. So the uniform free energy of the system, I'm going to write it down in Einstein's summation convention notation. Why? Because remember, it's s squared and s fourth, it's a scalar. The free energy for the system when it's uniformly in a uniform state, it involves summation over different components. So I want to write those things out explicitly so you can see how I get how I do the calculation. So I'm going to write it like this. So this is Einstein's summation convention. And so then if I now look for the minimum, so I'm going to differentiate the uniform part of the free energy with respect to S alpha, one of the Fourier components. So I choose alpha. Alpha is 17 or something like that. So then what I get is R0 as alpha plus or 1/4 U naught. And then I have to differentiate this thing, so you have to be careful. So it's 2s alpha times s beta times 2. And that gives me s alpha times r naught plus u naught s squared. So what that means is that when I'm above TC, then r naught is greater than 0, and the only solution is that s alpha is equal to 0. So that's the only solution above TC. But if I'm below TC, so that means that r naught is negative, then I have that s squared is equal to what I'll call m squared, and that is equal to minus r naught over u naught. So that's just setting this equal to 0. So remember, this thing has to equal 0 in equilibrium, and so that's how I get the condition. Okay, so So that's simple, and because this is mean field theory, so this thing here, I can think of this as expectation value of S squared. So this tells you that the direction of ordering is not specified. All I know is the magnitude of the ordering vector. So here we are. All I know is that the magnitude is the magnitude of the circle down here, and I don't know what the direction is. Okay, so that's fine. So what we're going to do now is we're going to choose a direction. And so what we're going to do is we're going to say that the spin is ordered along some particular direction, which was, say, the direction that an external field had been applied. So we'll say it's something like that, and then we'll say that in spin space, n is the vector 1 and then 0 in all the other components. So we're going to choose that as our direction, and then we're going to define the fluctuation by writing S of R is equal to the vector M plus phi of R. So this is the fluctuation. This is the mean field value. And what I'm going to do to make the calculation easy, since this n is proportional to m, it will be very convenient for me to put an extra factor of n in here. So I'm going to put this factor of n in there just to make the calculation easy. So that tells me what is the fluctuation. So the fluctuation is given by this formula here, and this phi is the fluctuation. Okay, so that's step one. We've just done, we minimized the free energy, and we found the spatially uniform state. Now we've calculated what the fluctuation, how it's defined. Now we're going to do a calculation for its correlations. So to do step two, what I'm going to do is we're going to split up phi into a longitudinal and transverse part. And we know we have to do this because we already saw that in the susceptibility there are longitudinal and transverse parts. So we're just going to simply follow that. So the longitudinal part is going to be the part that is parallel to n. And then the transverse part is going to be transverse to n. And since n is going along the one axis, what that means is phi perpendicular will not have any components other than phi 2 and so on and so forth. So I can write them down in the following way. So phi 1 is parallel to m, and phi 2 is going to be 0, and then phi 2, phi 3, up to phi a. So that way, this, because it has no components in the one direction, is going to be perpendicular to phi 1. So that's how we write down the fluctuation. So now we want to calculate the uniform free energy. So next we're going to calculate V of S. And so to do that, what I'm going to do is I'm going to write that the spin, our order parameter, is then m times n, and then there's a fluctuation in the n direction, and then there is the transverse part, which is also in S. And all of these things have been scaled so that the M appears on the outside of the vector. Yes.
Pardon, I'm wondering how we can get away with defining our SS this way, because of the fluctuation. Like, how can we assume that we can just scale the fluctuation by the order parameter, which varies? I guess I could follow if we just scaled it by some constant, but M is not a constant. So how?
No, I'm just putting M, taking M outside, and then whatever else is in phi one and phi perpendicular.
I mean, in the definition when we start with S.
But M is constant.
Right, yes.
Yeah,
Well, M is a constant.
M's a con. I thought that was the order parameter.
No, no, the order parameter is S. Its magnitude is M. Its direction is M.
Which varies by temperature, right?
Right, so M varies with temperature. You tell me, choose the temperature.
Yeah.
Okay, it's 3 degrees. Okay, you're done. M is a number.
Okay.
Did I answer your question?
I think so.
What part of it didn't I answer? What part of it didn't I answer?
Huh?
What part of it didn't I answer?
Whether I guess that we're assuming now that we're always at constant temperature moving forward.
Everything is a constant temperature. Right, so M does depend on temperature. So you have to tell me what R naught is. If R naught is greater than 0, M is 0. If R naught is less than 0, M is R naught of the unit. So there's the temperature.
Right.
Here's the number.
Which
Here's the temperature. Here's the M.
Right.
So
well, I guess I still would say that M is a function of temperature, but it's okay. I'll work on it. It's been a year since I've.
well, M is a function of temperature, but so what? It's just a number, right? It doesn't depend on space. It doesn't depend on direction. It doesn't depend on the radiative correction to the mass of the top quark.
I guess I'll work on it.
It's just a number.
Yeah.
So the game is this. Tell me what the temperature is. It's TC 0.8 of TC.
Yeah.
Okay. So now I know what R naught is. I know what unit is. I know what M is. And it's just a number. So it's just a number. So I've scaled. So S is magnitude M without any fluctuation. And if it has a fluctuation, you're going to pull out a factor of M, and then there's a constant function here, which I have to compute. I can always pull out a factor of M. Like I've just divided the phi by the value of M, 17.
Sure.
Okay, so I didn't do anything sneaky. There's nothing to get away with. Okay, there's plenty of things in this course where I'm pulling the wool over your eyes to get things done quickly, but this isn't one of these things. Okay, all right. So now let's compute the terms in the free energy. So the free energy goes like S squared and S to the fourth, as we can see up here. So I now need to compute what S squared and M squared look like. So S squared is going to be something proportional to M squared. And then what's inside here, I take the square of this, so I dot it with itself. So I'm going to get 1 plus 2 phi 1 plus phi 1 squared plus phi perpendicular squared. Okay, so that's what S squared of M squared is. And then the quartic term is going to be proportional to S to the fourth, to M to the fourth, and now I just have to square this. So I have a bunch of terms, 1 plus 4 phi 1 plus 6 phi 1 squared plus 4 phi 1 cubed plus phi 1 to the fourth plus phi perpendicular to the fourth plus 2 phi perpendicular squared plus 4 phi perpendicular squared of phi 1 plus 2 phi 1 phi perpendicular squared phi 1 squared. I got that right? Yeah. Okay, so that's the exact form. So now what I'm supposed to do is I take S squared over M squared, S squared over M to the fourth, and I plug them into here. And now there is something important here. See how M squared depends on U naught. Okay, it's U naught in the denominator. So when I put it in here, it's also going to come in, once I square it and so on, there'll be factors of U naught that come in and they get multiplied. You have to keep track of all of those M's the R naughts and U naughts. So if you do this, okay, and this is for you to check, what you now find is this. V of S is the following form. There's a constant piece, which looks like this, minus 1/4 R naught squared over U naught. Then there's a term, minus R naught M squared by 1 squared. And then there's a whole bunch of terms, which are like, say, phi 1 to the 4th, phi perpendicular to the 4th, phi 1 cubed. And remember that what I said was what we're going to do is our strategy is to only compute Gaussian fluctuations. We're only going to compute the second order. And when we compute the second order, that means I just throw away all attempts to higher than second order in the fluctuations. And the amazing thing is, there's only one term. There's only one term left. So that's fantastic. So these are all higher order terms. I'm just going to write a higher order term to plus higher order terms. Okay, so that's that. Now, that's not the only thing that contributes to the free energy. There's also the gradient terms. So the gradient term that's just grad S squared. So that's a half grad S squared. And now what's going to happen is, well, for grad S squared, well, all the constant pieces in S cancel out. The only thing that contributes to it are the fluctuation terms. So since they are they're just phi 1 and phi perpendicular, and they're orthogonal to each other, all I get then is m squared over 2 grad phi 1 squared and m squared over 2 grad phi perpendicular squared. So that's the gradient term. Yes.
I'm wondering where, okay, so we're referencing, I'm just wondering where the phi perpendicular square from in V of S.
Haha. Where phi- Yes. Where did it go? That's why you have to check this. Okay. It cancels out. Oh, it's not there. Okay, so this is not a misprint. It's a feature, not a bug. Okay. So this is the miracle. Now you can see why it should be like that, perhaps, because let's go back to our picture here. So this term over here, this energy that you get from phi 1, that's the longitudinal one. That is the longitudinal term where you take your order parameter, so it goes to here. Then I change its magnitude, so that's what the longitudinal thing is. When I change the magnitude, it's going up, and the energy is going up in this direction, it's going up in that direction. So that costs energy, and that's the thing computed. To translate this one, we already saw that there shouldn't be a cost. You can see it with our eyes. That's why it cancels. Okay. So, good question. I'm glad you're on your toes. All right. So let's now write down what the effective Hamiltonian looks like. So I'm going to call the effective Hamiltonian, I'm going to call it expectation, effective Hamiltonian H, but I'm going to call it phi. This now is a Hamiltonian that just depends on this phi order parameter, and it looks like this. M squared over 2 integral ddr, and then what I've got is grad phi 1 squared plus grad phi perpendicular squared And then I got 2 R naught phi 1 squared, and then higher order terms. So it looks like that. So that is the effective Hamiltonian that governs the fluctuations about the non-zero mean field value below TC. Any questions about that?
Figure how you come to this?
Calculated it.
Okay. Okay. You didn't. I guess I'm just.
I put this into the Landau free energy for the system. Okay. I put that into
And this is just the deviation from the mean field value. Like you didn't include that constant term.
No.
Yeah, that's okay.
No, because I don't care about it.
Right.
Why don't I care about it?
Because we are looking at fluctuations away from the mean field theory. And that won't contribute anything. Like that has no wave number dependence.
It has no wave number dependence. And why am I calculating this in the first place?
Because this is an energy, so we can say that this is equal to h bar omega, and we can get a dispersion relation once we take the Fourier transform with the right hand side.
Not quite. Okay. Remember what I'm trying to do? So let's go back to the strategy.
Correlation.
Exactly. So here's the thing. The reason I'm computing free energy or the effective free energy, the effective Hamiltonian, is because at the end of the day, I just want the correlation function. And the easiest way to do that is just compute the free energy and then just read it off. Right? You could do a calculation and compute it directly, but why bother when you can just get it for free? So that's that. So, any can I move on, or any other questions? Okay. So now let's do step 4. I mean step 3. Okay, so step 3, what I'm supposed to do is write this in Fourier space. Okay, well, it's easy to write in Fourier space because I can read off the correlation function. So let me write it in Fourier space. So here is my effective Hamiltonian for the fluctuations. And so it's going to be 1 over V sum over K. And then what do I have in here? So I'm going to write down the answer. So we know it's going to look like this. It's going to be 1/2 phi 1 Fourier transform squared times something. And we know that the thing that is going to be multiplying is going to be the inverse of the 2-point correlation function in the longitudinal direction. And then there's going to be a term which is the magnitude of the transverse correlation function as a function of k squared, and then it's going to be multiplied by something which will be the transverse correlation function as a function of k to the -1. So it's going to look, that's what it's going to look like, and you can see what it's going to be. So when I Fourier transform it, I'm going to get minus k squared, and I get minus k squared, and then I've got these terms over here. So now we can plug that, we can then read off that G parallel of k is going to be m to the -2 over 2 R naught plus k squared, and G perpendicular of k is equal to m to the -2 over k squared. So The longitudinal one, even when k is equal to 0, has a value. This one, when k goes to 0, this thing goes to infinity, or its inverse goes to 0, just as we saw before. And so this thing here, again, corresponds to this cost and energy in making a longitudinal fluctuation. There's no cost for the transverse fluctuation. So those are the correlation functions. These are all below TC for the longitudinal and transverse correlations. So now we can read off what is the correlation. So this one here has the same form of the correlation length as that we've seen before. It's something times something over k squared plus something over. And this thing over here is the correlation length to the -2 power. So what we can read off is that there's a correlation length. So for the longitudinal correlation function, there's a longitudinal correlation length that I'll call psi less than TC. I guess I should call it psi parallel, and its value raised to the power -2 is equal to 2 R0. And this is exactly what we found before when we were above, when we were for the system, for the discrete case, for the scalar case. So again, i.e. the correlation length in the parallel direction goes like t to the -1/2. This is below TC. And in the homework, one of the homework questions is to do what I did in class for the behavior above TC and below TC. And in fact, this factor 2 here is one of the things that comes up when you go below TC. So that's the longitudinal correlation length. Now when we look at the transverse correlation length, well, we can see that psi transverse to the -2 is equal to 0. There is no correlation. In other words, psi transverse is equal to infinity, and what this functional form means, the parallel decay in K space implies a parallel decay in real space for these transverse fluctuations. So this is a pole in G of K transverse. So this is a pole. Why? It's a pole because at K equals 0, there's a pole. And that pole corresponds to an excitation. So in general, if you compute correlation functions in systems, the poles of them correspond to particles. If there's a discrete set of poles, there's a discrete set of particles. That's how you read off the particle spectrum. So if you want to understand what is the particle spectrum of the standard model of particle physics, you compute the correlation functions and you find the poles, and that gives you the particles. And branch cuts give you other things. They give you like the continuous spectrum and things like this. So studying the analytic structure of correlation functions is in fact the way that we understand what are the excitations of systems, what types, what is their nature, and how do they behave. So,
sorry, can you elaborate on that point a little bit? How exactly does a pole in the correlation function correspond to a particle, as opposed to? I mean, I feel like we've been talking about waves, these perturbations, like waves of given wave numbers.
Well, have you heard of wave-particle duality?
Well, okay.
So waves correspond to poles.
Okay.
Waves correspond to particles.
But I feel like we've been seeing waves without poles, right? So why in this particular case, when there is a pole?
Well, we haven't actually. If you wanted to really see the wave, for example, I can see. So this thing, I can look at the poles of this.
Okay.
What are the poles of this? I have to look at the complex K plane.
Right.
Okay. There'll be plus or minus on the imaginary axis. So those poles, where those poles are, tell you about the masses of the particles. So here is a pole with K equals 0, and there's no mass. So it tells you that there's no. In this case, it tells you there's no energy for the particle. If I statistically, what is so the dictionary between particle mass and correlation length between statistical mechanics and quantum mechanics is that the mass is the inverse of the correlation length. So if this was a class on quantum field theory, what you would expect to see is a propagator who's like 1 over p squared plus m squared, where m is a particle. There wouldn't be a self-energy term here, comparable to term, which would tell you about the normalizations of the particle mass and interactions and things like this.
Okay, so in order to, like, if I didn't know this a priori, would I have to be thinking about this within the context of like an analogy to quantum field theory, or is there a way purely from statistical physics to naturally see that the poles correspond to particles?
Well, there aren't in statistical physics. You shouldn't use the particle language.
Okay.
Okay, because there aren't any particles.
It's
right?
just, yeah, there's no dynamic.
There's no things banging around.
Yeah.
Although they behave like particles, but they are just excitations of the system with certain wave numbers and frequency dependencies. Does that answer your question?
I think so.
I'm on the edge of something very mysterious.
Yes.
the connection between high energy physics and statistical mechanics.
Right.
Okay, and that connection is, I don't want to go into it in very much detail, because I mean, when I write down quantum mechanics, I write down e to the I over h bar times the action. When I'm doing statistical mechanics, I'm writing down e to the minus 1 over kt times the free energy, or Helmholtz, the effective free energy. So the action is like the integral of the Landau free energy. Okay, and so there's a transformation between imaginary time and temperature.
Yeah. Is this a Wick rotation?
Well, that's a name for it, but all it means is I just replace 1 over kBt with minus 1 over kBt with I over h bar times the integral dt is the same as the integral dx over kBt.
Okay.
But that's what it means.
Okay.
The whole idea of Wick rotation is a little bit careless, because you can only do a Wick rotation if there's no poles in the complex plane along the way.
I see.
And there often are.
I see.
So how you define quantum field theory is very ambiguous. But in any case, it's impossible to have something at 0 temperature anyway. So my view as a statistical mechanician is that quantum mechanics and classical mechanics don't have any independent existence other than as temperature going to zero limits of what you do in statistical mechanics.
That was very helpful. Thank you.
Okay, so okay, so I showed you this. So this was this was all a dirty trick. I showed you this in Gaussian theory. Okay, but you can prove this to all orders in perturbation theory. You can prove that this is exact. So even though we showed this. In Gaussian theory, but it's true beyond that. Okay, so let me just summarize what we've learned. So what we've learned is something very important, that for T less than Tc, transverse correlations are power law, not exponential. Below Tc, longitudinal correlations are exponential. Above Tc, longitudinal correlations are exponential, and above Tc, there are no transverse correlations. Because there's no transverse order point. And at Tc, longitudinal correlations and transverse ones are power law. So however far below Tc I am, I still have scale invariant transverse correlation functions, and what those things correspond to is the excitations of the system, which are the Goldstone modes. Okay, so there's that. Then let me add a comment, which was sort of what Janik was asking about. So if I have a quantum field theory, then I have the propagator of, say, a field. Looks like this, G naught. Okay, in Fourier space goes like 1 over k squared plus m squared, and where m is the mass of the particle which is given by the quantum field form. So that's what you have in quantum field theory. In statistical mechanics, what you have is the propagator, which we will call the correlation function. Of a fluctuating field phi, so that goes as 1 over k squared plus psi to the minus 2. And so we can kind of say that M in quantum field theory is analogous to 1 over psi in statistical mechanics. And people talk about Goldstone modes as being massless because in the field theory, it corresponds to zero mass here. We also talk about them as being gapless because they are, in terms of the energy, there is no energy gap between the ground states and these modes. Okay, so now I want to talk about rigidity. So let's now go back and I want to remind ourselves what we're trying to do here. We're trying to find a generic consequence of spontaneous symmetry breaking. So what our goal is now to identify another generic consequence of the spontaneous breaking of a continuous symmetry. So what we're going to do is what we're going to see is that the transverse power law correlations imply a rigidity of the order parameter. Okay, so let's to see that, let's go back and write down the effective free energy, the effective Hamiltonian for our system. So how do we do that? Well, we wrote it down a couple of pages ago, just over here. And so what I want to do is I want to write it down in terms of the longitudinal part and the transverse part. So there's a part here that is longitudinal. This part, squared phi1 squared, and 2r0 phi1 squared, that's the longitudinal part. And then the only transverse part, at least to this order, is this one over here. So let's write it down. So I can write this as the longitudinal contribution, longitudinal. And then there's the transverse part itself, and the transverse part itself looks like this. It's 1/2 the integral ddr, and then there's grad phi perpendicular squared. That's the only term, and it's multiplied by a number that I'm going to call R for rigidity. So that's what we've just calculated, and so this quantity R is going to be, we'll call that the rigidity, or maybe you'll call it the stiffness, whatever you like. And what this tells you is that if I make a change in the transverse component, it will raise the energy of the system. So let's think about what that means. So here is my system. The spins are all ordered pointing up like this. I take this spin over here and I hold it like this. Okay. I take this spin over here and I hold it like this. The energy cost is 0. Now I take this spin and rotate it. Okay. What's going to happen? I've now induced in the transverse direction, a change in the direction of the spin. So therefore, I've created a grad phi perpendicular square. And that has changed the energy of the system by an amount proportional to how much it changed over the distance of my arms. And that, so you can read off from that what the gradient is. And then whatever this coefficient R is, that tells me how much the energy cost was. So what it says is, if I have my spins like this, I hold this one over here, I rotate this one over here, that costs energy. There's another way to say it, which is if my spins are like this, and then I try to turn this spin over here, it pushes back. Okay, it's like a Hooke's law, just for the amount of rotation. Okay, that's the rigidity. That's the emergent spring. Remember in the first lecture of the course, I showed you what happens when something becomes a solid. And the particles, instead of being a fluid and floating around in space, all sit in a crystal lattice, and there are springs between them that tell you about the stiffness of the material, transmit the sound waves, correspond to the elasticity of the theory of the system. And those springs are what is emergent. And I just calculated for your spring. And it's exactly this. And how big that R is tells you how much force you have to push in order to rotate the order parameter by a particular direction. Okay, so this R we can interpret if you impose a rotation of the S at say x equals L relative to S at say x equals 0, that raises the cost of energy, raises the energy, which is another way of saying creates a restoring force. With spring constant proportional to this R. So that's what that term means, and we can read off that R is equal to m squared in Gaussian theory. So, and this also tells you the rigidity is a consequence of long-range order. Because if I didn't have long-range order, then m would be 0. If m was 0, there'd be no rigidity. So if m was equal to 0, no rigidity. So the longitudinal part over here, this part doesn't tell you anything about it. This doesn't change. Only the transverse part tells you about the rigidity. Okay, so now you know why I can move my cell phone by pushing it. Okay, let's give you an example. So if I have a ferromagnet, a Heisenberg ferromagnet, so that can order, so it can have some configuration which I'm not going to be able to draw very well. something like that. So this thing is called a spin wave. And it cannot happen in the T greater than Tc phase. It only happen in the low temperature phase where the system orders and points in a certain direction, and I can impose or thermally excite a spin wave. And then the coefficient that we call R is known as the spin wave stiffness. Okay, here's another example, which is a superfluid. In a superfluid, I have a wave function which is macroscopic. So psi of R, this is the wave function for 10 to the 24 particles in superfluid helium or in a superconductor. They all have the same wave function. Superfluid, which we'll talk about, is a state where a macroscopic number of particles all goes into one quantum ground state, one quantum state, a spatially varying state. So that state is described by a wave function that looks like this. This wave function describes not just an atom or a quark or something, it describes a whole fluid, a bucket of superfluid helium sitting on the table in front of you. Okay? And that macroscopic wave function is a complex number. And so this is the phase of the wave function. And so what happens is I can think of a superfluid as a complex number varying in space. And I can have this being the variation of the phase of the wave function. So the phase of the wave function can vary in space. So something like that. And so this thing is called it's called a phonon, or sometimes called a Bogoliubov mode or something like this. We'll talk about that. And in that particular case, R is the order parameter stiffness. Or the helicity modulus. And it also has another name. It's also called the superfluid density. So people measure the superfluid density. They can measure it in experiments. And that superfluid density turns out to be the rigidity of the wave function. Okay, why? Well, because I'll explain this to you next time. But roughly speaking, the velocity of a superfluid is proportional to the gradient of the phase of the wave function. So the kinetic energy of a superfluid is a half times rho times v squared. That's the kinetic energy density. Half rho grad phi squared. So what that means is that the kinetic energy, or the rho v squared, the rho in there is a superfluid density. But when I write the rho grad phi squared, then the superfluid density is multiplying the grad phi squared. So this is because a half rho v squared in a superfluid is a superfluid velocity is 1/2 rho times grad of the phase of the wave function times h bar squared over m squared. So this is the wave function phase, and the velocity in a superfluid is a h bar over m times the gradient of the phase of the wave function. And we'll talk about that next week. Okay, so this is superfluid velocity. And this is the phase of the wave function. And so you have this rho going in there, so this modulus is sometimes called the superfluid density. Okay, let's talk about another example. Let's talk about elasticity theory. Elastic solids. Okay. So what you do is you go back in time, and you go back to the 1850s. You go and read people like Cauchy and Green, Maxwell, whoever, and what you find is that if I have a crystal, that's the crystal lattice. But now each atom can be displaced by an amount, say like that. So that displacement is, we'll call U. So I take each atom, label it by I, or label it by its equilibrium position. Then I measure its displacement, so that's the thing shown in blue. Then from that, I can work out what is the free energy. So then I can write down a thing called the strain tensor. And the strain tensor is a tensor called Uij. It's a function of R. And that is dui by dxj plus duj by dxi, and there's a non-linear term there, but I'm not going to write it in, times a half. So that thing is called a strain tensor. It tells you how the displacement of an atom from its equilibrium position varies in space. And it's a tensor because they can vary in space in different ways. And then I can say, all right, so now I've got a fluctuation, but now it's not a fluctuation of a magnetic field or magnetic ordering or a quantum wave function. It's the fluctuation of a position. What is the effective free energy for that? And you can write it down in the following way. So the free energy is like this. So it goes like 2 times mu times u ij squared over r of r plus lambda ukk of r squared. Okay, so this is the u squared, the tensor squared. This is the trace of the tensor squared. And lambda and mu are coefficients. They have names. Cauchy and all those people from the 19th century gave them names. So this is called this one. Well, this one here is the static shear modulus.
That's summed over IJ.
Yep.
What are the subscripts of lambda u?
Lambda ukk. So summed over k. Repeated indices are summed over. All of this is with Einstein's summation convention. And so this is the static shear modulus, and this thing here is called the Lame coefficient, the A Lame coefficient. Actually, this is what I've written down here is only true for an isotropic solid. So this is assuming it's isotropic. So it would apply if I had, say, a disordered amorphous material that is isotropic, like a glass or a rubber or a gel, something like that. So that's what this refers to. If I have a particular material that has, say, gone into an orthorhombic crystal or tetragonal crystal, whatever you want, then the things that go in here are the irreducible representations of the point group symmetry of the crystal. But if it's isotropic, then those are the only 2 terms that you need. Okay? Cubic would probably be fine as well. Let me just think if it is true. Probably. Okay. All right. Now I want to talk about anomalous dimensions. Okay. So now the next question that we want to ask is, how does the stiffness scale? near TC. So what we know is that this stiffness coefficient, R, I don't have it on the screen there, but somewhere I have it, R equals M squared. Okay? And so you might say, well, M is the order parameter. So how does M go below TC? Well, M goes like T minus TC to the power beta. Right? We saw that last quarter. So you won't know what I'm talking about here. So just zone this out. So what you might expect is say, well, it's pretty obvious. R squared is equal to M squared. And we know that M, the order parameter, goes like minus T to the power beta for T less than 0. So I'm below TC. This goes like beta. And in Landau theory, beta, mean field theory or Landau theory, is equal to 1/2. So we saw that was true. So you might say, oh, well, it's pretty clear that R squared no scales as 2 beta. Okay? So that then tells you that R squared is proportional to minus T to the power 2 beta. Okay? And so actually I said R squared is equal to that, but I really mean that R is equal to that. Okay. You didn't correct me.
I was waiting for you to pass.
Yeah. Okay, so that's what you would guess. So this is wrong. So let's figure out why it's wrong. It's very interesting to see this. Okay, so why is it wrong? Well, the reason is very subtle. So the free energy density F has units of L to the minus D. This is free energy per unit volume. And so therefore, what we would know is that so therefore that would tell us that F should go like the correlation length to the power minus D in the critical region. Okay, so that's the thing. On the other hand, let's have a look at the grad phi perpendicular squared term. So we know that the rigidity comes from the grad phi perpendicular squared. So we know that this term also has dimensions L to the minus 2. And so therefore this thing also scales like psi to the minus 2. So since the free energy is going like R times grad by perpendicular squared, what that tells us is that the rigidity should scale like psi to the power 2 minus D. And that means it should go as minus T to the power nu to the power 2 minus D. Okay, all right, so this won't make sense to anybody who wasn't here last quarter. So now we know our scaling laws that we proved using the normalization group ideas. So we know that alpha plus 2 beta plus gamma is equal to 2. And we also know that gamma is equal to nu times 2 minus eta. So those are things that were discussed last time. And so in the end, what that boils down to is that R goes like minus T to the power 2 beta minus nu times eta, at T less than 0. So nu is a correlation length exponent. Eta is the exponent that tells you about correlation functions. Here k at Tc goes as k to the minus 2 plus eta, and then this is the correlation length psi goes as theta minus nu. So you can see that in general, Landau theory says that eta equals 0 in mean field theory, and so that's why we got this one conclusion here that R goes as theta 2 beta. It actually is corrected by some other things like that. Okay, so I'm going to stop there. I've got 3 minutes. I'm going to carry on. I'm not going to finish early. Okay. So the next thing is I want to just quickly talk about the lower critical dimension. And I can do this in a quick and dirty way. Okay. So what we're going to do is we're going to ask what is the stability of the ordered, i.e. rigid state. Just like we did at the beginning of this class, we looked at the stability of a Ising magnet, and we computed what are the fluctuations that destroy long-range order for a system which has a discrete symmetry. And we saw that these were fluctuations like little blocks of the system, and we computed from that that if I'm in 2 dimensions or above, I can have long-range order for a discrete order parameter system. That was the Landau-Pliles argument that we did at the beginning of the class. So now we can do a similar thing here. So let's have a look at what are the most dangerous fluctuations. So the most dangerous fluctuations are transverse ones. Why? Because it costs no energy to excite them. Okay, so let's have a look then at the 2-point correlation function for the transverse fluctuations. G is a function of R minus R prime. So what that is, we know that it goes like 1 over k squared. So it's the Fourier transform dk over 2 pi to the d of e to the I k dot r minus r prime. And then the transverse correlation functions go like m squared over k squared. So there's an m squared or something in there. Okay? So they look like that. So let's just look at that. Let's think about this very carefully. So lambda is the coarse graining scale. And the question is this integral finite? Because the most dangerous fluctuations are the ones that cause correlation functions to explode, and then that was the things that destroy order. That's how we did the calculation in the case of discrete symmetry. So let's see what happens here. So let's just do dimension counting. Think about this ddk. We know that this space is isotropic, so this thing is going to be spherically symmetric. So basically, because of spherical symmetry in d dimensions, G perpendicular of r minus r prime is proportional to the integral from 0 to lambda k to the d minus 1 dk divided by 1 over k squared times some e to the I k dot r. And so now let's not worry too much about that. Let's just look at this. The upper limit lambda is finite. That tells you the inverse of the lattice spacing, the ultraviolet cutoff. So that's a finite number. So this integral is going to converge at the upper limit because the upper limit is finite. But let's have a look at the lower limit. Okay, what happens at the lower limit? At this lower limit, this can potentially cause a divergence. So let's see why. Well, I've got k to the d minus 1 over k squared. So that is equal to k to the d minus 3. Okay, so if d is less than or equal to 2, then at the lower limit, the integral is logarithmically divergent or worse. So if it's d is 2, and this is 1 over k, set k equal to 0, if I integrate it, I get log k, but still log k as k goes to 0 is divergent. So it's logarithmically divergent. So it's divergent, and in d equals 2, it's log divergent. On d less than 2, it's power law divergent. And so what that means is that the ordered state is not stable in d less than or equal to 2. And so what that means is that if I have a continuous symmetry, can only order in d greater than 2. And that's the Wagner theorem. But here we're just doing it in Gaussian approximation, but it's true to all orders of perturbation. So this is an infrared divergence. So how many people here have know what Bose-Einstein condensation is? Okay, one of you. Two of you. Two? Anybody else know Bose-Einstein condensation? Eric knows it, right? Bose-Einstein condensation.
I know, I've heard of it, never worked it.
Okay, so two of you, maybe one of you. Okay. Okay.
It's been a while.
It's been a while. Okay. Bose-Einstein condensates exist. People got the Nobel Prize for creating them in cold atom systems, but they don't exist in 2 dimensions. Okay, you cannot have Bose-Einstein condensation at a temperature that's non-zero if you're in 2 dimensions. And the reason is exactly the same as the reason. When I write down a Bose-Einstein condensate, it's a macroscopic wave function. It's a system with a continuous symmetry, just like what we talked about. Bose-Einstein condensate is basically the same thing as a superfluid. Everything I said a few minutes ago about superfluids applies here too. So this proof that you cannot have long-range order in a system with a continuous symmetry in 2 or less dimensions applies also to Bose-Einstein condensates. You cannot order in 2 dimensions. So you can't have 2-dimensional superfluids. If you go to the APS March meeting, you will find, well, you may not find so often these days, but certainly would have done 20 or 30 years ago, many, many parallel sessions, all devoted to superfluid helium films and 2-dimensional superfluids and 2-dimensional superconductors. Do you work on a 2-dimensional superconductor?
I mean, like what?
Cuprates, okay? The cuprates are quasi 2-dimensional superconductors, okay? But they still have superconductivity, even though they are 2-dimensional. You have the copper oxide plane. You can make a single copper oxide plane superconductor, and it will superconduct. Okay, so why?
Maybe because the system's not actually infinite.
Okay,
That's my guess.
the system is not actually infinite. That's right. Okay, so where does this proof go wrong?
K to 0.
K to 0. So it's really not k equals 0. So let's just say this in the lab. You can see 2D superfluidity and superconductivity. But the reason is that when we do the integral dk, like this. This, remember, is really the sum over modes. Okay, I know there's going to be a class in here. Okay, so really the k equals 0 should really be k equals 2 pi over the system size, L. Okay, and then it's going to be diverging, logarithmic. So in order to destroy two-dimensional superfluidity, two-dimensional superconductivity, you need a system that is bigger than the galaxy, or the size of the universe, or something like that, for those fluctuations to be big enough to see these things. So you can approximately get two-dimensional superfluidity. You need a huge system to witness the destruction of 2D, let's just say 2D quantum window. Okay, that's today's lecture. So next time we will talk about superfluids and superconductors in 2 dimensions. We're going to talk about the cosmos-Thales transition. We're going to talk about topological order and vortices. Okay, so I'm going to turn off Zoom. I have a question I want to ask you, so I'm going to turn this off.